All right, today we're tackling a huge question. What's the real difference between our brains and the artificial intelligence we're building? It's this classic battle of biology versus silicon. And I promise you, the answer is way more fascinating than you might think. So let's just kick things off with a question that sounds, well, kind of ridiculous. Why is it that a 1-year-old, a baby, can do things like recognize a parent's face, or pick up a toy, or just figure out how to get across a room? Tasks that can bring a warehouse sized supercomputer to its knees. I mean, how is that even possible? What is really going on here? Well, to answer that, we have to look way past just performance and get right down to the source code, so to speak. The biggest difference isn't just about what brains and bots do, it's about what they fundamentally are. We're talking about a tale of two completely different architectures. And yeah, it really does start with the building materials. Our brain is what you could call wetware. It's this messy, carbon-based biological machine that's been slowly evolving for billions of years. AI, on the other hand, runs on pure silicon hardware. The software is a totally separate thing. You can copy it, you can edit it, you can install it. Just that one distinction, it changes literally everything. So what you end up with is this incredible set of trade-offs. The human brain is just mind-blowingly energy efficient, but our internal signals, they're actually pretty sluggish compared to a computer. AI signals zip around at nearly the speed of light, and you can copy an AI a million times with a click. But, and this is a big but, our brains are amazingly resilient, whereas an AI can sometimes be surprisingly fragile. Let's just pause on this one number, because it's absolutely staggering. 20 watts. The brain inside your head right now, the one listening to this, the same kind of brain that created civilization, runs on less power than a dim light bulb. That's insane. A supercomputer trying to do just some of what your brain does can need enough electricity to power a small town. It's just, wow. It shows you nature's unbelievable efficiency. Okay, so these massive differences in architecture, they lead to an even bigger divide. The way they actually learn. It turns out their methods for gaining knowledge are just as alien to each other as their physical forms. And this leads us to a really critical problem in a lot of AI systems. It's called catastrophic forgetting, and it's pretty much exactly what it sounds like. Imagine you spend a year learning how to play the guitar, and the very moment you get good, you completely forget how to ride a bike. That's what can happen to an AI. When it learns a new skill, it can literally overwrite the connections that held the old information. Poof, gone. So how do our brains avoid that? Well, you do it every night. You sleep. See, our hippocampus acts like this master librarian. It doesn't just jam new books on the shelf. It carefully indexes all the new information and files it away without throwing out the old books. An AI, on the other hand, often has to be manually forced to reread all the old data along with the new data over and over just so it doesn't forget. It's a brute force solution compared to our brain's much more elegant organic process. To really nail this down, let's use a fantastic analogy that researchers use. It involves a bear, a river, and some salmon. Okay, so this bear has learned two key things mean food: the sound of the river and the smell of salmon. Pretty straightforward. But one day, the bear has a bad ear and can't hear the river. An AI trained in a common way might get really confused. It sees the missing sound input, and its algorithm adjusts everything, potentially concluding that if there's no sound, there must be no smell either, and so no salmon. The AI bear goes hungry. But the real bear's brain is smarter than that. It knows that one piece of missing data doesn't just cancel everything else out. It still smells the salmon, so it knows the fish are there, and it gets to eat. And this fundamental difference in processing the world, it leads us to one of the most mind-bending ideas in the entire field of AI. It's something that completely flips the script on what we all think of as hard versus easy. It's called Moravec's paradox. And here's the core idea in a nutshell. All the stuff that feels completely effortless to us, like walking or seeing or grabbing something, is computationally massive and incredibly hard for a computer. And all the stuff we find really difficult, like higher math or chess strategy, is often computationally trivial for a computer. And the key is, it's not about how hard it feels to us. It's about the raw computing power it takes to do it. Think about tying your shoelaces. It feels like nothing, right? For a robot, that task is a monumental feat of perception, fine motor control, and constant physical feedback. Why are we so good at it? Well, because our brains have had hundreds of millions of years of evolution to become absolute Olympic champions at moving around and sensing the physical world. But abstract stuff, like logic and math and grandmaster level chess, that feels really hard to us. We struggle. But for a computer, which is literally built for logic and calculation, those tasks are computationally cheap. They're easy. You see, abstract reasoning is a new trick for us, evolutionarily speaking. We're still the new kids on the block. The guy who came up with this, Hans Moravec, he put it perfectly with this quote. It's really humbling when you think about it. The stuff that feels like genius-level work to us is really just a new trick we're learning. The things we take for granted, that's our ancient superpower. So, if our greatest intelligence is so deeply tied to our physical bodies and how we interact with the world, what does that mean for AI? Well, it points to this growing idea of embodied AI. The theory is that if you want to develop anything close to human-like thinking, an AI can't just be a brain in a jar reading text all day. It needs a body. It needs sensors, cameras, hands. It needs to learn from cause and effect in the real world, just like we did. So after all of this, after comparing brains and bots, where does that leave us? Are we in some kind of competition? No, not at all. This isn't a story about replacement. It's a story about collaboration, about a hybrid future. See, the key isn't to ask who's smarter. It's about recognizing that there are different kinds of smarts. We bring creativity, common sense, and the amazing ability to learn from just one or two examples. AI brings the raw horsepower, blinding speed, perfect precision, and the power to sift through data on a scale we can't even imagine. They're not competitors, they are the perfect complements. And that's why the goal here shouldn't be to build a perfect digital copy of a human mind. I mean, honestly, why would we want to perfectly replicate all our own cognitive biases, our limited memory, and our tendency to get distracted or tired? No, the real goal, the actual prize, is to build AI that fills in our gaps. An AI that can use its perfect logical consistency to check our biases, one that uses its massive memory to augment our own. It's about creating a partnership where the whole is so much greater than the sum of its parts. But for that partnership to actually work, we humans need to develop something researchers are calling intelligence awareness. Basically, we have to stop thinking of AI as just an imperfect version of ourselves that's slowly catching up. We need to understand and respect it for what it is, a fundamentally different, almost alien kind of intelligence, with its own unique strengths and its own bizarre weaknesses. And all of this brings us to one final crucial thought. For decades, the big question has always been, can machines think? But maybe that's just the wrong question. Maybe the more powerful and way more exciting question we should be asking is this: how can they help us think better?